Welcome and hello. This is a video exercise using the FHWA hydraulic toolbox. I'm titling this exercise Median Ditch Inlet. So we're going to be using the median ditch drop inlet calculator as well as the channel calculator. And I'll bring up my problem statement to the screen right here. The question asks to find how many grates are required to capture 100% of the flow. And as you can see here in the diagram, we have a median ditch with some dimensions. So we need to capture that flow using this particular grate. It's the 30% tilt bar grate, only 1 foot by 1 foot. So that's going to be part of the issue. The location will be inlet on grade, made of concrete, and then some of the other slopes and widths are provided in this diagram. Right, so these are the numbers that we're going to be using in our calculators. So if you want to follow along, these are the numbers to use. I'm going to pull that off to the side here. And what I have is my hydraulic toolbox. We're going to start with a couple calculators, starting with a new channel analysis, and then after that, a new median slash ditch drop inlet calculator. Analysis is what it's called. The reason that I've got a channel analysis as well is because as soon as I open up the median ditch calculator, it's going to ask me for a channel. We can create a new channel or use the channel analysis channel that I've already created. I'm going to go ahead and define the properties of the channel, which is effectively the median ditch, but I want to do so separately in its own calculator. And I also want to rename it. So instead of channel analysis, I'll give it a different name that's a little bit more meaningful. All right, so channel analysis, I'm going to go right click, rename. I'm going to call it channel 0-1. You'll see why that is the case because the median ditch inlet, I'm going to rename this one. I'm just going to call it grate 1. All right, so channel 0-1 is going to be the channel upstream of grate 1. It's going to be flowing from 0 to 1. So let's get started with the channel. I'm going to right click, open up the channel data. I'm going to bring the cross section of the channel back onto the screen here. So it looks like it's a triangular shaped channel, or sort of two triangles, but unfortunately we can't utilize any of the pre-built shapes for our channel just because of the shape. It's not exactly a trapezoid. It's not exactly a triangle, definitely not a circle. So we're going to have to resort to a custom cross section. So click on cross section for your type and then click on the define button. This is where we're going to define the cross section data for our median ditch. The slope of the channel, we were given that it was 0.04. So 4% longitudinal slope down the ditch towards the grate. Next up is the number of cross section points. So let's take a look here. We've got 1, 2, 3, 4, 5 points should be enough to define this cross section. So I'll change the 3 to a 5 and then tab off. Okay, so I've got 5 rows in my table here. Now going back to the cross section again, let's see here. We need to define the station and elevation values. Let me bring this down here so I can see it a little better. Okay. All right, so I'm going to start this the far left station number 1 at station 0, and then the stationing will just increase. In fact, let's go ahead and knock out the stationing first. So if this first point here, we could just call it points 1, 2, 3, 4, and 5. If this is 0, then point 2 would be TS plus 0, which is 2 feet. And then because S sub x1 and S sub x2 are the same slope of 10%, then we know that the horizontal distance is the same. So that means this is going to be 1 foot to 0.3, 1 more foot to 0.4, and then, of course, 2 more feet to 0.5. So as far as the stationing goes, I'm going to type in 2, 3, 4, and 6. Okay. Next up is the elevation. And we know that the lowest elevation point is going to be 0.3 right here. So I'm going to arbitrarily just set 0.3 to a nice round number for the elevation. I'll say it is 10 feet. Okay. So now I need to define the elevation for points 2 and 4. Those will be the same, as well as 1 and 5. Those will also be the same due to the symmetry of our ditch. All right. So if we have a run of 1 foot at a 0.1 slope, that would just be an increase of 0.1 foot. So plus 10 would be 10.1. That's for 0.2 and for 0.4. And then from 0.4 up to 0.5, it is a run of 2 feet, and then the slope is 0.03, this S sub x3. So that would be a vertical rise of 0.06 added to 10.1 is going to give us 10.16. So that's the elevation for point 0.5 as well as point 0.1. All right, there we go. Manning's N value, we were not provided Manning's N, but we were provided that it is concrete. So I'm going to use 0.013. Concrete can sometimes be 0.012 or as high as 0.016, kind of depending on the quality of the concrete and whether or not there's sediment. But I'm going to go with 0.013 for my Manning's N in this exercise. I'm going to click on plot just to double check that the general shape is correct. Of course, the vertical axis is exaggerated. It's probably something more like that. But okay, looks good. And then click OK. All right, so the only thing I need to do remaining in this channel calculator is to define the flow or the depth. Now, I don't know the flow, but I do know the depth because our diagram shows that the water is all the way up to the top. So the depth, the maximum depth here would be between the lowest elevation of the cross section and the highest elevation of the cross section. Basically, the elevation from point 1 minus the elevation 0.3. So let's revisit our data real quick. 10.16 minus 10 is going to be 0.16 feet. So I'm going to type that in for the depth, 0.16, and then click on calculate. And then this is just a warning message that says the critical depth computed for the input parameters entered exceeds the channel capacity. Therefore, the hydraulic toolbox assumes vertical walls at the end of the cross section. And that's fine for what we're doing. We're not too interested in the critical depth. And the Froude number is greater than 1, so that makes sense. That checks out. 3.368 feet per second. And the most important number for us is the flow rate, which is 1.145 CFS. So this is the flow rate that's going to be entering grate 1, or I should say approaching grate 1. And then we'll see just how much of that flow is actually intercepted by 1 foot grate 1. All right. So that's what we're going to do next. I'll click OK. And before I forget, I'm going to save my project, project2.hyd, save. Okay. And then here is my grade 1 data. I'm going to double click to open up that calculator. And then for the channel data, now I'm just going to select channel 01. This is the channel that leads into grade 1. So everything is good and ready to go there. Below that, I have the design depth and flow. I can change this if I want, but I don't want to do that. Everything is good there. So I'm done with the left part of this dialog box. On the right half of this dialog box, we have inlet data. So what we were provided is that it is inlet on grade. It's 30% tilt bar, and the size of the inlet grate is 1 foot by 1 foot. All right, so let's go inlet on grade. That's good. And then the grate type, let me scroll down here to 30-degree tilt bar. And then the size is going to be 1 foot by 1 foot. All right. So with all that done, I'm going to click on compute inlet data and boom, it's telling me basically the same message I saw before. So I can ignore this. I've read it and it's coming up multiple times here. All right, here we go. Out of a total of 1.145 CFS, here are our results. 0.509 CFS has been intercepted, and that means 0.636 has bypassed. So we need more than one grate. The efficiency was only 44%, and I tested out with the other types of grates. All of them are basically around 45 to 50%, but it's the size of the grate that's really killing us here. So anyway, this should be interesting. What we're going to do now is create a second channel and a second grate, which will basically be duplicated copies of the previous channel and grate, except the channel will have a lower flow. Our channel from grate 1 down to grate 2 is going to have a flow equal to the bypass flow from grate 1. Does that make sense? All right, so I'm going to click OK here, and then OK. I'm going to save just to be safe. And then what I'm going to do is make a duplicate of channel 01, just like that. But I'm going to rename it now. And instead of 01, I'm going to go 1-2 and then open that data up. Okay, I'm just going to have to deal with this warning message. Instead of a depth here of 0.16 feet, what I'm going to do is type in a flow rate equal to 0.636 CFS and then click on calculate. Okay. So we're good to go there. Let's take a look at the plot. Okay. Okay, so the water surface has come down a little bit. This is the same geometry we were looking at before in channel 01, but some of that flow was intercepted, which is why the water surface elevation is no longer at the top. Okay, so there's that. We are done with this channel 1-2 calculator. I'll click OK. Now it's time to make a copy of Grate 1. Right click, duplicate, and then right click, rename. I'm going to go Grate 2 now. And then right click, median ditch drop inlet. That's the calculator we're opening up. And plenty of warning messages. All right, now for the select channel in Grate 2, what I want to select is channel 1, 2. So it already has our design flow of 0.636. That's what was bypassed Grate 1. Everything else is set. As you notice, we have the exact same inlet properties. That's the power and efficiency of making a duplicate of our channel calculator and our ditch median inlet calculator. Okay, so I'm going to click on Compute Inlet Data, and it's giving me a warning. And finally, we have our results. Very cool. So out of 0.636 CFS, it looks like 0.397 CFS was intercepted by that Grate 2. And then what was bypassed was 0.239 CFS for an improved efficiency of up to 62.5%. So Grate 1 was only, 45% efficient, something like that. And now the efficiency of Grate 2 is 62.5%. But anyway, the number that we're interested in most is the bypass flow, which is 0.239 CFS. So we've used two grates already. Out of those two grates, which started at 1.145 CFS, now we're down to a bypass of 0.239 CFS. All right, let's repeat this process one more time. Hopefully the third grate will be enough to capture this remaining flow of 0.239 CFS. So I'll click OK. I'll click OK to the warning, and then right click and duplicate channel 1, 2. Right click. Let's go ahead and rename it now. We call it 2-3. All right. Double click to open that up. OK. Now the only thing I need to do here is enter the flow, and this is going to be 0.239 CFS. Click on calculate. All right. So this is ready to go when we create and select Grate 3 for edits. So we can click OK. I'm going to right click on Grate 2, click on duplicate, and then right click and rename. This is going to be Grate 3. Double click to open up Grate 3. Okay. And then here is our editor. I'm going to change the channel now to 2-3. It has our design flow of 0.239 CFS. I'm going to click on compute. And sure enough, we have 100% interception rate. All 0.239 CFS has been intercepted. Bypass flow equals 0 CFS for an efficiency of 1.077. Okay. Well, I expected the efficiency to be 100%, just say 1.00, but I can't explain that. Well, good. So that is it. That answers our question. Our original question was right here. How many grates are required to capture 100% of the flow? In our case, it is 3 grates. Of course, there weren't a lot of assumptions that went into this. We didn't assume that there was a new additional flow added to the channels after the grate. And this particular analysis probably could have been performed just using one channel and one grate if we continuously change the numbers. But I kind of like preserving the data. So we have a distinct flow rate in channel 01, 1, 2, and 2, 3. And then we also have distinct efficiencies and capture percentages in grate 1, 2, and 3. All right, well, that was it for this exercise. We talked about the median ditch drop inlet calculator as well as the channel calculator.